Ladies and gentlemen, welcome. My name is Deněk Hanzálek, and this is the 56th talk of the scheduling seminar. So today we have the 3 years anniversary of the seminar because we started in March 21 during COVID crisis, and today we are like 55 talks later. So many nice people spoke up to now from different corners of the world, both from America and China and US. And in average, we had like 700 views per talk, including both online views on Zoom and YouTube, and also offline views on YouTube. So in total, we had like 32,000 views on YouTube and more than 6,000 views on Zoom. The most popular talk was the first one given by Jan Karlek and David Schmois, which reached nearly 3,000 views on both channels. So here you have a list of the leading talks, the most viewed talks in different seasons. We had like 3 years and 3 seasons in each, spring, fall, and winter. We don't have talks during summer. And here are the stats. So different talks are on horizontal axis, and on vertical axis you have either a cumulative number of participants per talk on Zoom, or a peak number of participants, because people are progressively joining and leaving. So these numbers differ. So for the red curve, you have the scale on the right side, and for the blue bars, the cumulative number of people on the left side, right? So that was on Zoom, and here on the right side you have it on YouTube, but it's cumulative during several years, because it's also including offline views. Again, we have a cumulative number and peak number of viewers concurrently. So you see, for example, that on YouTube we have like 20 viewers online, and on Zoom we may have like 50 viewers in average. And here, since these are cumulative numbers, the later talks are in advantage since they could have been observed during 3 years, while the recent talks have been observed just during the last months, right? And here we have number of views on YouTube per month. So this number is slowly growing because there are more talks available. So there are more views, and we have like 1,000 views per month. Okay, so that's it. So I may stop sharing now because I need to invite our speaker today. And the speaker is André Rossi. He is coming from Universite Paris-Dauphine. He made his PhD in 2003 on robust scheduling with Mireille Giacomino. Currently, he is co-head of the Department of Mathematics and Computer Science. And his interests include optimization with uncertainty, namely in scheduling and communication and transportation network design. And as a hobby, he enjoys reading Stefan Zweig, for example. And that's it. So, André, I'm very happy to have you here. The floor is yours. Please go ahead.
Thank you very much, Deněk, for the nice introduction. So I will start sharing my screen. I hope you can see and you can hear me correctly.
Yes.
Otherwise, let me know. Yes.
We see it and we hear it, yes.
Okay, thank you. So it's my pleasure to present this work, which has a lot of collaborators, mostly from University of Nantes, also from Amiens and from Bordeaux. So this talk is about maximizing stability assessment of the assembly line balancing schedules under uncertain task durations. And I will present different variants of this problem and different approaches to address it. So as an introduction to explain what we want to do here, suppose that we have a set V of n tasks with a duration Tj, which is a positive real number for all j. We are also given an acyclic precedence graph, GVA, given here. And we have a set of m workstations with a given cycle time C. And we want to assemble a product. And to assemble one product, we need to perform all the tasks that are given here. And the duration of the task is also displayed here on the precedence graph. And to do this, we need to assign these tasks to workstations. So we are m workstations that we can represent like bins, for example. So we have 6 workstations in this example. The cycle time C is 10.5 units of time, which means that when we will start assigning the task to workstation, the sum of the duration of all these tasks cannot exceed 10.5 units of time. So we call this constraint the cycle time constraint. So as an example of such a schedule, we can, for example, say that tasks 1 and 2 will be allocated to the first workstation. And then in the second workstation, we will process only task number 3. And to do this, of course, we also had to respect the precedence relation, which means that if there is a precedence relation between 2 tasks, then these 2 tasks can be put in the same machine, or maybe the first task I should be in some workstation, and J that should be processed after the completion of I should be allocated to a workstation with an index which is larger than or equal to the index of the workstation of I. Okay, so we can, of course, represent a solution using a Gantt chart, which is a more usual way to represent a solution. And we can check that this solution is feasible because each task is processed by exactly 1 workstation. The precedence constraints are satisfied, and also the cycle time constraint is satisfied because we do not exceed 10.5 units of time on each machine. So this problem is very popular already. So it is called SALBP for simple assembly line balancing problem. And there are 2 classical variants that have been introduced in the book of Skoll. So the first variant is SALBP1. It is to minimize the number of workstations for a given cycle time. And you can view this as a problem which is very close to the bin packing problem. The second variant, SALBP2, is to minimize the cycle time for a given number of workstations. And in that case, the problem resembles the scheduling problem PM precedence Cmax. So these are the 2 classical variants. And here I would like to present the variant where the tasks are subject to uncertainty in terms of durations. So here we mentioned some of the reasons that could motivate this study. For example, we have, in the context of manual assembly lines, the performance of operators that implement the task will depend on their work rate, the skill level, fatigue, and motivation. This can change over time. Second, we may have product specifications as well as workstation characteristics that may change during the line cycle time. And finally, we can also undergo various delays and micro stoppages when tasks are executed, and this can have an effect on the duration of the tasks. So to model this, we're going to use the following notation. So V tilde is a subset of V. And this given subset is the subset of tasks whose duration is uncertain. So here we assume that only a subset of tasks can have durations that can vary. So T is the vector from 1 to n that contains the nominal task times, which means that if we have no uncertainty, then each task should have a deterministic duration. We define the set omega as the set of all the xi vector, where xi is an Rn vector, where xj is 0 for all the tasks that are certain. Okay, so because the tasks that are certain have a fixed duration. Otherwise, xj can be any real number. And this is the set of processing time deviation. So for a given solution to the problem, like the one I presented earlier, what is the minimum task duration increase that compromises feasibility? So that's the key question we want to address here. To answer this question, let's f of t be the set of the feasible solutions to the problem with respect to some particular t vector. And we can observe that since any decrease of task processing cannot compromise solution feasibility, it is sufficient here to consider only non-negative task time deviation, which means that from now on, I will assume that Xj is always positive or zero. Okay, because I have no problem in case where the duration of the task decreases, but I can violate feasibility when the task duration exceeds, for example, is such that, for example, one workstation exceeds its working time, its cycle time C. So in that context, we're going to use the stability radius, which is a famous measure, as follows. So for a given solution S that belongs to a big F of t, then the stability radius is the largest value of epsilon, such that S has to stay in F of t plus xi, which means that S is still feasible for any xi vector that belongs to B of epsilon, where B of epsilon is the stability ball. So more precisely, the stability ball is the set of all the xi vector in omega, such that the norm of xi is less than or equal to that epsilon. Of course, the norm that is going to be used here will have a lot of impact on what we can model. Okay, so with this definition, then the stability radius is determined as the value of the radius of the greatest closed ball B, called the stability ball, representing the deviations of the uncertain task nominal processing time for which S remains feasible. And the norm that is used in the stability ball here plays an important role, as we're going to see. So we're going to see two different norms. First, we start with the L1 norm. So if we define B using the L1 norm, what we have is B1 of epsilon. And now you see that the epsilon, vector epsilon, is such that the sum of the absolute value of its component should be less than or equal to epsilon. This induces the definition of the stability radius using the L1 norm, which is denoted by rho 1. And that's the same definition, but now Xi has to be part of B1. And we also consider the L infinity norm, which is B infinity. So now we just make sure that the largest absolute value of an entry of that vector has to be less than or equal to epsilon. And this gives rise of the rho infinity stability radius. So these definitions, these notions have been introduced by Sotskov, and for example, in that work, but in many other works. So that's quite a general notion that we have been applying in that particular context. So we can view these two different norms as two ways of measuring the stability that the solution S can have with respect to the increase in the duration of the tasks. So before I give some example and illustration of this, there are two properties I would like to state. First, say that for any solution S, which is feasible, and Xi that belongs to big omega, such that Xj is equal to rho infinity of St for all j which is uncertain, we have that S belongs to big F of t plus Xi. This simply means that even when all the uncertain tasks have a nominal duration increased by rho infinity, the solution remains feasible. So this is why we use the term of stability. The property 2 is a connection between the two norms, which states that rho infinity of any solution is always less than or equal to rho 1 of the same solution S. And this is simply due to the fact that the stability ball B1 of epsilon is always a subset of B infinity of epsilon for any epsilon because of the property of the two L1 and L infinity norms. Okay, so now let us see what is the impact of selecting one or the other norms in terms of the different kind of disturbances that the solution can stand. So if we consider this solution and the stability radius in the L1 norm, the question is, what is the stability radius? So we need to find the smallest increase of the duration of a task that can compromise feasibility. And here this happen with workstation 3 or workstation 6. For example, if task 8 sees its duration increase by more than 1.5 units of time, then this solution is unfeasible. So we have that row 1 is equal to 1.5, because if any task has an increase which is less than or equal to 1.5, then we can be sure that this solution, this particular solution, will remain feasible. Now, suppose that we use the L infinity norm. So now we assume that all the different tasks will have their duration increased by the same amount, which is rho infinity. And in that case, since here the non-working time on workstation 3 and 6 is 1.5, and there are 3 different tasks on workstation 3, you see that each task here can have its value increased by 0.5, while still maintaining feasibility. So in that case, in case of that particular solution, the rho infinity value is just 0.5. Okay, so they have different values and they correspond to different kind of hypotheses in terms of increase of the duration of the tasks. So now we are interested in computing the stability radius of a particular solution. So some notation here will be useful for that. So VKS is the set of tasks assigned to workstation K in solution S. And W tilde S is the set of all the workstations, such that there is at least one task on that workstation that is uncertain. Okay, because V tilde KS is equal to VKS inter V tilde. So this is simply the set of tasks that are allocated to workstation K and that are uncertain. So with this notation, we can see that the stability radius in the L1 norm is defined by the workstation K among all the workstations that process some uncertain tasks, that minimizes the non-working time, which is C, minus the sum of the Tj, where J belongs to VKS. Okay? And for computing the stability radius in the L infinity norm, then we use the same quantity here in the numerator, but we divide this quantity by the number of uncertain tasks on workstation K. So the workstation that minimizes this quantity will set the value for rho infinity. So now, what is interesting, or what we would like to do, what is new, in fact, compared to what was introduced by Soskov, is that we would like to not only study a solution and find its stability radius, we would like to build the solution that maximizes the stability radius. So we can offer the decision maker with the largest possible protection against uncertainty. So we define 2 problems. Problem P1 is to build a solution to the simple assembly line balancing problem that maximizes rho 1, which is the stability radius in the L1 norm. And problem P infinity is to do the same. So we want to maximize the stability radius, but now in the L infinity norm, and this is problem P infinity. So both of these 2 problems can be shown to be NP-hard, even in the particular case where V is equal to V tilde, which means that all the tasks are uncertain. And we can show this by reduction to the bin packing problem. Now I will propose some mixed integer linear programming formulations for these 2 problems. So here are the decision variables that I'm going to use. So the first decision variable is rho 1. It's the stability radius optimal value. It should be maximized. So in this talk, I will only present maximization problems. And of course, this decision variable occurs in problem P1 only. So rho infinity is the stability radius in the L infinity norm, which occurs only in the P infinity problem. And what is common to both problems is the xjk variable. So xjk is set to 1 if and only if task j is allocated to workstation k and 0 otherwise. We also have the ak variable, which is set to 1 if workstation k processes at least 1 uncertain task. And this variable will be used for problem P1 only. Finally, we have the xjk variable that are continuous and non-negative variables that represent the duration increase of task j, where j belongs to V tilde, if it is allocated to k, where k is some workstation. and we will need these variables for p infinity only. So with these decision variables, we can propose the mixed integer linear programming for problem P1. So for problem P1, we want to maximize row 1. The first constraint simply states that each task J should be allocated to exactly one workstation. The second inequality here is the cycle time constraint, because the total working time or working load of workstation K should be less than or equal to C, the cycle time, which is given here. Then what we see here is to enforce the precedence constraints, okay, because here capital A is a set of precedence arcs. Then these constraints, xjk less than or equal to ak, just means that if some task j, which is uncertain, is allocated to workstation k, then this should force ak to take value 1. And the last inequality here poses an upper bound on row 1, and it can immediately be seen that if ak is equal to 0, then we'll have that row 1 is less than or equal to c, which is an obvious upper bound. But in case where ak is equal to 1, then we see that row 1, just as in the earlier formula, will be less than or equal to c minus the working time on that workstation. And the rest of the model here is composed of domain constraints. Okay, so this is the first mixed integer linear program that we proposed in 2016 to model problem P1. But now, if we want to maximize the stability radius using the L infinity norm, then we have a different formulation, which is less efficient, by the way. So again, it starts with the same constraint. Each task should be allocated to exactly one workstation. And then here you see that in this inequality, we say that the increase in the duration of task J when it is allocated to workstation K should be less than or equal to UB infinity. So this is a constant, a big M constant, we could say, times xjk. So we need to know an upper bound on the stability radius to be able to use this mixed integer linear program. So we'll discuss this later and see what we can do to produce the best possible UB infinity value before we can build this product. Then here we have that row infinity. The objective function is equal to the sum of the xjk for all j. And these variables are not used, in fact, when j is a certain task, as can be seen in the next constraint. So in this constraint, which is again the cycle time constraint, we see that we have the contribution of the tasks that are allocated to the workstation k, plus the contribution of the extra time of the corresponding tasks, provided that these tasks are uncertain, okay? Which means that the xjk variable for the task j that are certain are just not interfering with these constraints, which is what we want. The rest is classical, so that's precedence constraints and the domain. Okay, so we have presented two different mixed integer linear programs for problem P1 and problem P infinity. Now we would like to solve this problem better by trying to set some xjk variable to 0. And to do this, we're going to use some existing ideas. For example, we are going to present the allocation intervals that were proposed by Patterson and Albrecht in 1975. This allocation interval results from the fact that we have precedence constraints, and because of these precedence constraints, then we can reduce the workstations that are able to process a particular task. So for any task j, qj is its interval, its allocation interval. And qj is written as lj uj, where lj is the smallest index of a workstation, and uj is the largest index of workstations that can process a task j. And as shown in Patterson and Albrecht, we can initialize, we can compute this qj as follows. So we have this integer and this over integer that involve P of j, which is the set of all the direct and indirect predecessor of j, and S of j, which is the set of all the direct and indirect successor of j. And so after computing this, which can be computed offline very easily, we can safely set all the xjk variable to 0 for all j in V and for all the workstation k that are not in qj. Okay, so this is, of course, very helpful in the mixed integer linear programs that have been shown earlier for P1 and for P infinity as well. But now we would like to produce allocation intervals that are even tighter than this, and we will spend some effort to try to improve over this. So to tighten these allocations, there are already some very good ideas that have been proposed. One of these ideas is, again, due to Skoll and Baker in 2006, where the idea is to consider or to replace the M workstations here by a single machine. And this single machine has a working time, which is equal to the number of workstations M times the cycle time C. So here, if we have 6 workstations, we can represent this as a succession of 6 workstations that form a single machine, like this. And we're going to exploit the precedence constraints that exist in that particular setting. So to do this, I will introduce the following notations. So for all task I in V, let tau I be a lower bound on the earliest starting time of task I in that single machine. And let zeta I be an upper bound on the latest completion time of task I, again, in that unique machine. So step 1 is first to initialize a value for tau I. And to do this, we can solve this classical single machine scheduling problem with one machine, ready times, and we want to minimize the Cmax value, the maker span. And we do this for all the tasks J that belong to Pi, so the predecessor of I, to compute tau I. So to do this, we must give values for the Rj, the ready times. And that's why we should solve this problem by topological order of the task I. So every time that I solve this problem, all the predecessors of the task I should have been processed already, so I can access the Rj value. In step 2, I want to improve the tau I value even further. We can observe that if tau I is strictly larger than C times floor of tau I over C, then Li, which is the lower bound on the index of the workstation, is just 1 plus floor of tau I over C. And at least one direct predecessor of I is allocated to Li. So C tau I can be improved by the following formula. That's the maximum between its current value tau I and C times floor of tau I over C plus the minimum duration of one direct predecessor of task I. Okay, so this is one way to improve the lower bound tau I and make it bigger. Then step 3, this is a second improvement for tau I. So we define Q as floor of tau I over C. And if task I starts at time tau I, then it is processed by workstation Q plus 1, as we saw previously. Now, if we have that ceiling of 1 over C times tau I plus Ti is strictly larger than Q plus 1, then task I cannot be allocated to workstation Q plus 1 just because the tasks are not preemptive. They cannot span over 2 different workstations. So in that case, this means that this task has to be moved to the next workstation. And so we should improve tau I and set it to Q plus 1 times C. So this is a second way to increase tau I even further. So everything that has been presented here for tau I also works for zeta I. Remember that zeta I is an upper bound. So we perform the same step, but we consider the reverse precedence graph. So the same ideas lead to good results also for upper and lower bound. And there is a final tightening that we propose, which is inspired from a paper of 2003 by Flezar and Hindi. And it consists in adding new precedence constraints. So if I belongs to V and there exists J in V minus Pi, such that zeta J minus Tj is strictly less than tau I plus Ti, in that case, then we can be sure that task J must complete before task I can start, and consequently, we can add a new arc, Ji, to the precedence graph. So why is this useful? Because after adding this arc, I can repeat all the previous computation for tau I and zeta I, and this arc can only help strengthening or narrowing the interval of allocation. Okay, so now that we know how we can set a lot of xjk variable to 0 thanks to the allocation interval, I would like to present some upper bounds that can be useful in that problem. So first, let me introduce UB11, which is natural upper bound on row 1. UB11 is simply equal to C, the cycle time, minus the longest uncertain task, which is obviously an upper bound for row 1. There is another one, which is called UB12, which is computed by allowing task preemption. So we can observe that in the best case, all the certain tasks are processed by the same workstations. And so the maximum number of workstations that process certain tasks for C units of time is key, equal to sum of the Tj for all the certain tasks only, and we divide this by C, and that's the number of workstations. After doing this, the remaining m minus k workstations should process a load which is equal to the load of all the certain tasks minus the load that has been processed by the key workstations plus the contribution of the uncertain tasks. So we have a remaining number of m minus k workstations that should share the remaining load. And there are two different cases that can occur. First case, the m minus k workstations share the same load, and in that case, this common load can be easily computed as follows. Okay, the sum of the Tj corresponds to the sum of these two sums here. And the second case is when a single workstation processes all the remaining certain tasks, letting m minus k minus 1 workstations for processing the uncertain task with a common load also. And so we can summarize these two subcases using this notation. So UB12 is equal to C minus the minimum of these two quantities that correspond to common loads. Okay, so we have different strategies to produce upper bounds for this problem. So in fact, producing upper bounds is very important for problem P infinity, because this problem, as if you remember these constraints, requires that we know a good upper bound UB infinity before we can solve this problem. So of course, UB infinity can be set to the minimum of UB11 and UB12, but we can do better. And here we propose a bisection method to improve any existing upper bound UB infinity. So to attempt this given UB infinity value for improvement, the input is UB infinity that we want to try to minimize. It can be initialized to a mean of UB11 and UB12, for example. And we also need LB infinity, which is a lower bound on row infinity. This lower bound can be set to 0 if we have no knowledge about any feasible solution, or it can be found by a heuristic, and I will present this heuristic in a moment. The output is, of course, UB infinity, which is a possibly better upper bound on a row infinity. And this bisection method is, in fact, based on the allocation interval. So this is where it is interesting, because we can connect the two different aspects of the problem. So this is a bisection method to improve UB infinity. So we set L to LB infinity, the original lower bound. U is a copy of the original upper bound. And here epsilon is just a parameter to control precision. So while U minus L is strictly larger than epsilon, we do the following. But I would like to stress that the L value here is not exactly a lower bound. It is a lower bound on the upper bound. Okay, it's not a real lower bound on the stability radius value. So as long as the gap between U and L is strictly larger than epsilon, then delta here is the average value of L and U. And for each uncertain task, we set the duration of the task Tj to Tj plus delta. And having done this, we compute the allocation interval of Qj. And then there are two cases. If L of j is less than or equal to U of j for all j, then there is no particular problem, no contradiction. And in that case, we can set L to delta. Otherwise, this means that there exists at least one task j such that the allocation interval is empty, and in which case we must update U to delta. Okay, and after this, we need to restore the original tj value. So tj is equal to tj minus delta. And we can start a new loop if needed. And when this while loop terminates, then we have a new value for UB infinity, which is capital U here. Okay, so this works quite well, but we wanted to take one step further, trying to really produce the best possible upper bound for this problem. And this is why we turn to dancing ball field decomposition. So we take the milk formulation for P infinity, which is not so efficient for the many reasons I gave. And we say this is the initial compact formulation, and we want to propose the dancing ball field decomposition for the sake of having better bounds. So the extreme points that will be represented as columns are the workstation patterns. We will initialize columns with a feasible solution. So again, I refer to the heuristic I will present in a moment. In the pricing subproblem, we should define a task assignment, maximizing the sum of the reduced cost for the sake of having a solution of the pricing problem, which is attractive in the sense that it should help the master problem having a better bound. And the decomposition process will in fact create one subproblem or one pricing subproblem per workstation. So all this decomposition here is introduced in this paper. So I don't know if it is worth giving a lot of details, but we will consider a subset of the inequalities that define the problem P infinity. And we will decompose it as follows, because it can be seen that here we can decompose these constraints per workstations. And so a pattern is a subset of tasks that can be allocated to a given workstation. So the new variables here are the lambda kr variables. So each lambda kr variable is associated to a particular pattern that will be applied to workstation k, and r is some extreme point. Okay, and these variables are the same as before, but now there is a new index r, because this corresponds to the particular points r. So I don't want to go into the detail here. I just want to notice that there are some dual variables that are in brackets here, and these dual variables will be used in the subproblem. But before I present the subproblem, I would like to present one valid inequality that we found to reinforce the formulation of the master problem. So it says that rho infinity has to be less than or equal to this quantity. So here, if lambda kr is equal to 1, this means that the pattern is applied to workstation k. And in that case, since this is equal to 1, then rho infinity will be less than rho kr. And rho kr is the local stability radius on workstation k. Otherwise, if the corresponding pattern is not used, this is 0, and we simply have rho infinity less than or equal to ub infinity, where ub infinity is a constant, which is the best upper bound that we know before we solve the dancing ball field decomposition, which means that this constraint in that case is not active. And again, we associate a dual variable to this new inequality of the master problem that will be taken into account by the pricing subproblem. This is the pricing subproblem. Again, I think it's quite difficult to give details in another presentation. Only thing you have to see here is that what we want to find is to define the pattern. So we are looking for the xjk variables and also the xjk variables, and also, of course, the local stability radius. So the pricing subproblem is NP hard, and unfortunately, we had to address it using a MILP solver at each iteration. Again, we can find an easy way, or not an easy way, but a nice way to improve the pricing subproblem. This is thanks to a paper of Peters and de Grave from 2006. We can reinforce the precedence relation by adding the following valid inequalities to each pricing subproblem. So if there is a precedence constraint between I and j, and there exists another task L, which is a successor of j that can be allocated to workstation k, then we can immediately see that it is possible to allocate tasks I and L to workstation k, but if we do so, we also have to allocate workstation j to the same we also have to allocate task j to the same workstation. Otherwise, the solution would not be feasible. So these inequalities are efficient because, as you can see, they are very sparse. Only 3 decision variables are involved in each inequality. And so after solving the pricing subproblem PSK, then if its value is PK, and this quantity, which is the reduced cost, is strictly positive, then this means that we found a new column to be added to the master problem. Okay, so this is a classical way to add new columns and try to discover a good upper bound for the problem. Okay, so after talking about upper bounds, I would like to say one word about how we can find lower bounds, which mean feasible solution to the problem. To this end, I want to propose a multi-start greedy heuristic that considers the workstations in order and tries to allocate a task j such that all the predecessor of j has been scheduled, so we can understand this as a task j is processable. Second, we must be sure that when we add these tasks, we do not violate the cycle time constraint. Third, we can also check that the selection of j does not cause the stability radius to be less than LB, where LB is the current best solution. Okay, because we want only to discover new solutions that are better than the current one. And finally, we also want to be sure that the current workstation belongs to the allocation interval of Qj. So if by applying this strategy, we are able to find a feasible solution, then we can update the lower bound. Otherwise, then we should forget about the current solution and a new attempt should be made. What makes this randomized is that plenty of tasks satisfy all these conditions, so we can select the one we want randomly. And so we can repeat this process of trying to build a solution many, many times. And this is quite efficient. And of course, we can also implement the same strategy backward, in the sense that if we reverse the precedent graph, we can also try to fill the different workstations from the last one up to the first one. So this also is efficient sometimes. So this heuristic is generic in the sense that it applies to all the problem P1 and P infinity that have been proposed. And it returns very fast, quite good solution. Now I would like to show some numerical results. So this table focuses on how efficient are our strategies in closing or setting to zero some x, j, k variables. So we are going to compare 2 strategies. So PA means Patterson and Albrecht. So this is what happens in case where I use the original Patterson and Albrecht strategies to set some x, j, k variables to 0 versus the new allocation intervals that results from the 4 steps that I presented you to how to improve these results. So this is the number of fixed variables. So if we do not use the lower bound heuristic that I presented, then we can close 379 variables for that group of instances. But if we use the new allocation interval, you see that we can fix more variables to 0, which is better. And also, if we use the lower bound, we can also increment or increase the number of variables that we can set to 0. And this nice effects is also visible when we use the new allocation interval. Here, this column CG time is the running time of the column generation algorithm with a limit of 5 minutes, so 300 seconds. And this is the number of arcs that are added in average for all the instances of that group. You can see that it is very, very low. So usually it's very difficult to discover new precedence graphs or new precedence constraints by applying this method. However, what is important here to stress is that with this method, we are able to close a lot of variables. And this, of course, will accelerate the convergence of the mixed integer linear programs that we proposed. Again, now if we want to see how efficient is the Dancing-Wolfe decomposition in finding good upper bounds, we are going to compare the upper bound obtained by the compact model solved with Cplex after 5 minutes. So we have an upper bound, which is the UB compact. And when we run the Dancing-Wolfe decomposition for an additional 5 minutes, we have a new bound, which is UB-DW. And the deviation dev-UB is computed as follows. So on the 7 following set of instances, we have spectacular improvements, okay? Because when the upper bound decreases, we are very happy, and we see that it decreases by a very large amount. But this is true only for 7 subgroups. In average, this is an improvement which is much more modest, only 9%. And it can be seen that when for these instances where the improvement is large, we manage to find this solution fast, before the 300-second time limit. So in fact, the Dancing-Wolfe decomposition is efficient for those difficult instances and of course fails at improving the upper bounds that are already very good with the compact model. Okay, so I would like to present a new variant of the problem, because when we present this work, sometimes we receive some justified criticism, and because there are 2 limitations, I think, at least 2 limitations in the use of the stability radius. So first, we could observe that with the stability radius in the L1 norm, it is possible that the whole extra duration may affect a single task, which may be considered very unrealistic. And this defaults, this flow also affects the stability radius, which is expressed in the L infinity norm. In that case, what we can have is that the maximum duration increase, this rho infinity value, is always the same. And this is true for the very short and the very long tasks. And also this can be considered a bit unrealistic, because we tend to think that a long task may have a duration increase that should be larger than the duration increase of a very small task. And so to circumvent this, we introduced the stability factor in this paper from 2022. Now we're going to talk about the maximum rate of increment of the nominal processing time applied for any uncertain task without compromising the feasibility of the corresponding line configuration. So instead of talking about stability radiuses that can be expressed in seconds or in unit of times, now we'll talk about stability factors that will be proportionality factors that apply to the duration of the uncertain tasks. So this is a new way of measuring stability, which is not based on the radius. So to illustrate this, again, let us revisit the same example as before, where all the different tasks are uncertain. And now you can see that the stability factor F here is equal to 1/6, which means that you can increase the duration of all the tasks by 16% without violating the cycle time constraints. So we revisited all the theory, and now we have a stability factor measure, which is inspired from the Sotskov work. So that's the same here, but instead of a stability ball, now what we have is a stability hyperrectangle, h of epsilon t. And you see that now the constraint is that Cj should be less than or equal to epsilon times Tj. Okay, so time was not involved previously. The computation of the stability factor is, again, very, very similar. Okay, so instead of dividing by the cardinality of the number, or the cardinality of Vsk that we had for the stability radius in the L infinity norm, now we divide by the sum of the Tj. Again, this is good news because the mixed integer linear program for maximizing the stability factor is very similar to the one of P infinity, but this constraint here, which is the constraint that enforces the cycle time, becomes this. So you see that now I had to multiply Cjk by Tj, which is not a problem, by the way, because Tj is a constant. And now we have, of course, a change in the sense that Cjk is now a factor. It's no longer a unit of time. Now we also have a variety of different upper bounds, because we also need upper bounds on the stability factor, just as in P infinity, where we needed a bound on the stability radius. So here we have a very natural one, which is that UB1A is equal to C minus lambda I1 over lambda 1I, where lambda 1I is simply the longest uncertain tasks. There is a second one here, which is based on the fact that the total amount of work that the workstation can carry out together is upper bounded by M times C. And this can be written as follows. So 1 plus F, which is a factor, times the contribution of all the uncertain tasks, plus the contribution of the certain task whose duration cannot increase, should be less than or equal to this upper bound. And we can immediately deduce an upper bound on F, which is UB1B. Again, we wanted to have very, very tight results. So that's why we spent some effort with the UB1C and UB1D that are both based on the pigeonhole principle. So we can say that there exists at least one workstation that processes at least gamma 1C equal ceiling of cardinality of V tilde over M uncertain tasks. Then we let pi be a permutation of the set V tilde such that the tasks are ordered by increasing duration. So it can then be deduced that the total processing time due to uncertain tasks in that particular workstation is at least lambda 1C, where lambda 1C is the sum of the processing time of the uncertain tasks, and we take only the smallest one because we are using this permutation. And so we can again use the same formula. UB1C is C minus lambda 1C over lambda 1C. Finally, we can also observe that at most ceiling of sum of the Tj over C, where we consider only the uncertain tasks workstation, have a load equal to C due to certain tasks only, which leaves, again, M minus this number of workstations to process uncertain tasks. And again, by applying the pigeonhole principle, we know that there exists a workstation that processes gamma 1D uncertain tasks, where gamma 1D, by the way, can be shown to be larger than or equal to gamma 1C. And as a result, there exists a workstation that processes at least gamma 1D uncertain tasks, whose total load is again written as follows by using the same permutation. And so there is a fourth upper bound on F, which is again based on the same kind of idea. Okay, so this is how we can find good upper bounds that are needed for us to implement problem PF. There are some results also that show that there is no equivalence between the problems, which means that it is useful to study the three problems independently, because unfortunately there is no direct connection between all these problems. First, we can show that problem P infinity and PF are not equivalent. To do this, we're going to use 5 tasks, 2 workstations, and the following duration for the tasks. All the tasks are uncertain, and the C value for the cycle time is 8 units of time, and there is no precedence constraint. So we can build the first solution S1, for which we can see that F of S1 is equal to 1, because obviously we can increase the duration of all the tasks by 100% without violating the cycle time. And here the rho 1 value is equal to 1. I think this is not rho 1, sorry, here this is rho infinity. Okay, the rho infinity value here is equal to 1, because if we add 1 to the duration of all these tasks, then we reach 8. So this is infinity here, not 1, sorry. Now, if we have a look at solution S2, so this solution is different. It can be seen that now the stability factor is less, but the stability radius is larger. And so since solution S1 is optimal for stability factor maximization, because it reaches the lower bound, the upper bound UB1A, then it can be seen that these two objective values, so rho infinity and F, are just not equivalent. We can similarly show that P1 and PF are not equivalent with a different example, which is nearly the same. Only difference is that now the last task, task C5, is certain, so it's not uncertain, and we can also compare these two solutions and found out that solution S1 is optimal for P1. Okay, because here there is a stability radius in the L1 norm, which is equal to 4, whereas S2 has a better stability factor value because we go from 1 to 5/3. Otherwise, there are sometimes good news. The good news is that when V tilde is equal to V, then problem P1 and PF are equivalent. So in that case, there is no need to have a bad formulation, because remember that PF has a bad formulation in the sense that it uses Xi, JK variables, and this is less efficient. We can also discover some natural properties that are based on J minus and J plus. So J minus is simply the shortest duration of an uncertain task, whereas J plus is the longest duration of the uncertain tasks. And the property says that if the stability factor of a given feasible solution S is f of S, then its stability radius in the L infinity norm is at least Tj minus times f of S. And of course, you can immediately derive a corollary, which says that if the stability radius in the L infinity norm of a given feasible solution S is rho infinity of S, then its stability factor is at least rho infinity of S divided by Tj plus. So if we have a look at the computational results for the stability factor maximization, if we consider a set of 25 instances that are up to 297 tasks and 60 workstations, then here we can see that when the number of uncertain tasks increases, so here we have 1/4 of the tasks being uncertain, half of them are uncertain, and then 3/4 of the tasks are uncertain, you see that the number of optimal solutions that we can find in 10 minutes will decrease a lot, very significantly. Also, the average CPU time to address these 25 instances is going to increase vastly also, and so is the gap. So the gap increases when the number of uncertain tasks increases. So we can immediately see that the problem gets more and more difficult when the number of uncertain tasks increases. And also what is not shown in this table is that it gets more difficult, the problem gets more difficult when the number of precedence constraints decreases. So the more constraints we have, and the easier the problem. So some conclusions about these different problems. Maximizing the stability radius for the problem SA-LBP is difficult. We try to formulate 3 variants for this problem, but still there are some instances that we cannot solve with 50 tasks. In terms of method, we have different research directions that we could take. For example, we may use the upper bounds that we have, because now I think we have quite tight upper bounds, to design a branch and bound algorithm instead of using a mixed integer linear program. Also, we presented the dancing ball fit decomposition in this work, and a natural extension is to propose an exact approach of the branch and price family. There are other problems also that can benefit from this. For example, when we have incompatible tasks, so 2 tasks that cannot be processed in the same workstation for some technological reasons, for example. We can also think of capacitated variants of the problem, so they can easily be handled by the mixed integer linear programs, for example. And also, we have applied this to the transfer assembly line balancing problems, where instead of having only 1 task that can be processed, then we can process many tasks in parallel. Okay, and finally, we should think of alternative model to handle uncertainty besides stability, because that's not the only indicator, even if we spent a lot of time developing this. That's it. So thank you very much for your attention, and if you have any question.
Okay, thank you, Andrea, for your very informative talk. So now I'd like to open discussion. Should you have any question or remark, don't hesitate to unmute your mic and speak. You should be able to do so, right?
Sure.
So if nobody wants to start, then I would like to ask, did you consider, for example, to use also constraint programming or some alternative frameworks to model this problem? Because what I have seen, you have many precedence constraints and like, let's say, the cycle time, which I think gives the room for edge finding and these pruning techniques that should be able to to make the domain smaller or?
Yes, so this is a very good idea. We did not try it yet because we are not very optimistic about the use of constraint programming. The reason is that when we start having a lot of constraints, the mixed integer in our program are very efficient, in fact. And so we are currently struggling with those instances where the precedence constraints are very rare and the precedence graph is rare, is sparse, and we have a lot of symmetry problem. So the reason why we did not spend much time in trying to use, for example, these nice solver like Choco or other solvers like this, is that because the big challenge for us is when we have very sparse precedence graphs.
I see. Okay. Thank you. So any other question? If there is no more questions, so let me thank you once more. And I would like to remind you that the next talk will be by the end of May, because the 1st of May is holiday and the other talks have been postponed. So we will have Matthias Mnich from Technical University Hamburg on 29th of May. And he will speak about new support size bounds for integer programming applied to make-span minimization on uniformly related machines. So thank you, André, once more for your nice and informative talk. And I remind to others that the next seminar will be on 29th of May. Okay?
Thank you very much, Dinek, and thank
Yeah.
you all the audience for attending.
Yeah. Thank you, André. Bye-bye.
Bye.